We now discuss about Newton's laws of motion. Before discussing Newton's laws of motion, it is important to realize what brings a body into motion. From our examples of daily life, we realize that in order to bring a body into motion, we require something which is called as a force. So force is nothing but an external agent that might bring a body into motion. Or if a body is moving, then in order to stop the body or in order to bring the body into rest, we definitely require something which will try to retard the motion of the body. We are associated with the concepts of displacement, velocity, acceleration, retardation, and all other parameters of motion. As we know the parameters of motion, we are now in a state to analyze what causes motion or what produces motion in a body and what actually brings a moving body to rest. Before discussing Newton's laws of motion, it is important to know about the state or the inherent state or the inherent property of a body, which is called as inertia. Now, inertia is an inherent property. It is an inherent property of every object. It is a property which is available to every object of this universe. Now, by inherent property, I mean that this property is always present. It is a characteristic feature of every object. Now, the inertia is nothing but the property associated with the situation where a body is in a state of rest or a body is in a state of motion. So, Newton's laws of motion, starting from the first law, the second law to the third law, they describe inertia and the force that tries to bring a body into motion or retards a moving body and finally tries to stop it. So Newton's laws briefly describe force, inertia, and another important concept which is called as momentum. A force you can call as an external agent that is necessary for producing motion in a body, or it is necessary to bring a moving body to rest. And momentum is actually the quantity of motion possessed by a body. So these three terms are somewhat interrelated. These are three different physical quantities. They are interrelated, and Newton's laws of motion continues to the description of all of these physical quantity. Before Newton, many scientists tried to analyze motion. They realized the different parameters of motion. They could realize what is velocity, what is acceleration, what is retardation, and other parameters of motion. But a force is trying to bring a body at rest into motion. And when a body is in a state of motion, it actually continues in that state. But what actually brings a moving body to rest could not be analyzed prior to Newton. Galileo started with a correct observation. Galileo realized that it is necessary to bring a body to motion. The necessary external agent is the force. So force is definitely required to set motion in a body. Unless and until there is an retarding force, or unless and until there is an obstruction, or unless and until there is an external force that tries to bring the moving body to rest, the body will continue its state of motion. So it becomes easy to realize from all the observations that we can associate with motion that if a body is in a state of motion, it will maintain its state of motion unless and until it is compelled to stop by some external force. Or if a body is at rest, it will maintain its state of rest unless and until it is compelled to move by some force acting on it. Once a body starts a motion by some external force being applied on it, it will continue in state of motion. So, Newton's laws of motion, basically the first law of motion describes inertia, and in order to break the inertia, that means in order to bring the moving body to rest or in order to set motion in a body, the force is a necessary criteria. Force can be therefore described as an external agent that can change the state of rest or the change of motion in a body. So we come up with Newton's first law. First law of motion will state this, that if a body is in a state of rest, or if a body is in a state of motion, it will continue to remain in the state. It will maintain its state, it will maintain its inertia, which is the inherent property of every object. So if a body is in a state of rest, it will remain at rest. Or if a body is in motion, it will maintain its state of motion. Unless an external force is applied. Now again, you must remember that in order to start the motion, an external force is required. In order to stop the motion, an external force is required. An external force that supports the motion will initiate motion in the body. It will produce motion in a body which was at rest. And when the body is in the state of motion, there is no requirement of any external force. But in order to stop the body, definitely an external force that will obstruct its motion is necessary. So in either case, it is the force which is necessary. And this force will definitely try to overcome the inertia of the body. So inertia is either inertia of rest or it is inertia of motion. So inertia is nothing but it is a tendency of a body to maintain its state of rest. So inertia, you can say, it is a tendency of a body to remain at rest that we call as inertia of rest, or it is a tendency of a body to remain in motion, which is called as inertia of motion. And in order to break that inertia, we require what is called as external force. Say for example, a bicycle is set into motion by moving the pedal. The bicycle continues to move, but in order to stop the bicycle, some brake is required, a braking force is required, and definitely the braking force together with the friction between the tires of the cycle and the road will bring the moving bicycle to rest. Now this is an observation which is associated with any vehicle which is in motion. In order to set a car or a automobile in motion, we require the power of the engine. The engine generates a power which produces a force and sets the vehicle into motion, and in order to bring the vehicle to rest, we require the application of brakes, which is nothing but a force that is supported by friction between the tires of the vehicle and the road, and ultimately the object or the vehicle stops. So in order to start the motion, we require a force. The force is not needed in continuation of the motion. That means while the body is moving, once it has started motion, a continuous force may not be required, but in order to stop it, a force is again required. So Newton's first law of motion, which describes inertia and also describes force, it does not give any mathematical analysis of force, or it does not give any mathematical analysis of inertia, but it simply describes inertia and it describes force. So inertia is nothing but it is a tendency of a body, it is an inherent property of a body to maintain its state of rest. So whenever it tries to maintain its state of rest, we call it as inertia of rest. Whenever the body tries to maintain its state of motion, we call it an inertia of motion. And force is nothing but it is an external agent that tends to change the state of rest or the state of motion in an object. So in the first law, if a body is in a state of rest, it will remain at rest. If a body is in motion, it will maintain its state of motion. Now while saying that it maintains its state of motion, means that it continues in its state of motion, which is nothing but uniform motion. So maintaining its state of motion means it is in a state of uniform motion. Uniform motion means it is not accelerating. Whenever an acceleration is produced, an external force is again required. So whenever we say that a body in motion is in a state of motion, it means that it is maintaining uniform motion or a motion with a constant velocity in a specific direction. With constant velocity. Or you can say that it is uniform motion along a straight line. Uniform motion along a straight line. Now this is extremely important here to realize. The body will maintain its state of motion means that it will remain in a uniform motion along a straight line unless external force is applied. Once we apply external force, definitely the velocity does not remain constant. It might accelerate, it might get retarded, and so you cannot say it as inertia of motion. So inertia of motion is nothing but the state of motion whereby the object is maintaining a constant velocity. That means it is in uniform motion along a straight line. That means it is not accelerating, it is not retarding, it is maintaining its constant speed also, you can say. So Newton's law of motion does not explain the acceleration or the retardation of the body due to the application of continuous external force. If the force is continuously applied on the moving body, it might accelerate. If an obstruction is produced continuously, it might retard until it comes to rest. So whenever we describe first law or whenever we analyze first law, it is noteworthy that if a body is in a state of rest, it will remain at rest, and if a body is in motion, it will continue to maintain its motion, uniform motion along a straight line until an external force is applied. So inertia of rest and inertia of motion associated with a body and the necessity of force to break the inertia is discussed in Newton's first law. What we realize is that inertia is dependent on the mass of a body. So we can say that mass is a measure of inertia. Now by saying that mass is a measure of inertia, it means that more massive the object is, more is its inertia, and for lighter objects the inertia is definitely less. Greater the mass, greater is the inertia. And lighter body has less inertia than a heavier body. In other words, you can say that more is the mass of a body, more difficult it is to move the body from rest or stop the body if it is initially in motion. And so we say that mass is a measure of inertia. We can come across various examples whereby we realize how mass is a measure of inertia. For example, if we compare the motion of a bicycle and a car, definitely a car has more mass as compared to bicycle. And suppose both are moving with the same speed along a straight line, more braking force is required to stop a car as compared to a bicycle, because the mass of the bicycle is quite less as compared to that of the car. It is difficult to set a loaded trolley in motion than an unloaded trolley, and you can say that it is similarly difficult to stop a loaded trolley than an unloaded one if both are moving initially with the same velocity. If you compare the masses of cricket ball and that of a tennis ball, a cricket ball has definitely greater mass as compared to a tennis ball. So the cricket ball will acquire much smaller velocity than a tennis ball when both are pushed with the same force, are pushed with the equal force for the same amount of time. And if the cricket ball and the tennis ball are moving with the same velocity, it will be definitely more difficult to stop the cricket ball, which has more mass, as compared to the tennis ball, which has lesser mass. We can come across, or we can take various examples of inertia of rest. Inertia of rest, if you remember, it is intrinsic or inherent property of a body. And inertia of rest means that if a body is at rest, it will remain at rest unless an external force is applied to change that state of rest. Inertia of rest, there are various examples that you can easily refer in your textbook, but still let me give some examples. So suppose a carpet or a curtain is given a sudden jerk, or it is beaten with a stick, the dust particles immediately fall off the curtain or the hanging carpet. Now this is because the part of the carpet or the part of the curtain where the stick has struck, that part will come in motion at once, while the dust particles which are settled on it will remain in state of rest due to inertia of rest. And so the sudden jerk that is given to the curtain or the carpet will allow the dust particles to fall off, because the dust particles cannot acquire the sudden motion provided to the curtain or the carpet. And this demonstrates inertia of rest of the dust particles. Suppose a passenger is sitting in a bus and the bus at once comes into motion, then definitely the person sitting in the bus or standing in the bus will definitely lean backwards or tend to fall backwards. This is a very common scenario that we come across in our daily life. Now, what happens is that the lower part of the body of the passenger in the bus or in the train is definitely in close contact with the floor of the bus or the floor of the train. As the train or the bus starts moving, the lower part of the passenger's body will share the motion at once, but the upper part of the body, due to inertia of rest, will try to maintain its state of rest and cannot share the motion simultaneously, and as a result of which the passenger, the lower part of the body moves ahead and the upper part is left behind, and the passenger tends to lean backwards or tends to fall backwards. So there are many such examples where we can realize inertia of rest. A very common example is the motion of a card on an empty tumbler. Now suppose you have an empty tumbler or a glass over which you have placed a card, and the card contains a coin. If you suddenly strike the card will fly off and the coin will definitely fall into the glass tumbler. Now this is because a sudden motion which is provided to the card will set it into motion, but due to inertia of rest, the coin will fall into the container. It will not acquire the motion immediately that is provided to the card. Due to inertia of motion, the coin will fall into the tumbler. So there are many such examples where we can realize inertia of rest. A very common situation is that on shaking the branches of a tree, the dry leaves or the fruits fall down, because when the stem or the branches of the tree are shaken, they come in motion, when the fruits or the dry leaves due to inertia of rest remain in the state of rest, and thus they fall off. Now, as far as inertia of motion is concerned, a body is in a state of motion, continues to be in a state of motion with the same speed, in the same direction, in a straight line, unless an external force acts upon it. And this is what we call as inertia of motion. We can see similar examples that are associated with inertia of motion also. So, for example, when a person is standing in a moving bus and the bus suddenly comes to rest, the passenger or the person will definitely lean in the forward direction. This is because the lower part of the body of the passenger, which is in contact with the floor of the bus or the train, will come to rest, but the upper portion of the body, due to inertia of motion, has a tendency of moving forward, and so the person will lean in the forward direction when the bus or the train suddenly stops. If you throw an object vertically upwards while you are sitting in a moving train, say for example you throw a ball vertically upwards in a moving train, definitely the ball will come back to your hand, because at the moment the ball was thrown, the ball was in motion along with the person and the train, and due to inertia of motion, during the time the ball remains in air, the person and the ball move ahead by the same distance. This makes the ball to fall back to the palm of the person. You have obviously seen that whenever an athlete is trying to perform in long jump event, he or she often runs before taking a long jump. But the reason behind this is that by running, the person brings his body in a state of motion, and when the body is in a state of motion, it becomes easier for the person to take a long jump. And this is also an example of inertia of motion. So there are so many examples that we come across in our daily life that demonstrates why mass is a measure of inertia, what is inertia of rest, what is inertia of motion, and what is the role of force in order to stop a body or in order to produce motion in a body. Now we discuss about momentum. To be precise, we will discuss linear momentum, the momentum acquired by a body when it is moving along a straight line. Now, before understanding what momentum is, from our common experience, we definitely note that if two bodies of different masses are moving with the same velocity and they are brought to rest in the same time, the force needed to stop the heavier body is definitely more than the force needed to stop the lighter body. So definitely the mass, the velocity of the body togetherly will account for the amount of motion produced by a body or the amount of motion possessed by a body. But on the basis of comparison, we have to remember how their mass is comparable and how their velocity is also comparable. So I repeat again that if two bodies of different masses are moving with the same velocity, here we consider that the velocity of the two bodies are same. For example, a car and a bike are moving with the same velocity. A car has greater mass, a bike has comparatively lesser mass. In order to bring the car to rest, we need a more powerful braking force as compared to the braking force that is required to stop the bike. Similarly, you can say that if there are two bodies of the same mass and they are moving with different velocities, then in the same time, more force is required to stop the faster body than the slower body. So if you are comparing two objects of the same mass, two identical motorbikes moving with different velocity, one moving with the velocity of 100 km per hour and one moving with the velocity of 70 km per hour. Definitely, in order to stop the bike moving with 100 km per hour, more braking force is required as compared to the braking force required to stop the bike moving with a speed of 70 km per hour. So whenever we discuss about the quantity of motion possessed by a body, or what we call as linear momentum, it is the contribution of mass as well as the contribution of velocity that analyze the momentum of the body. So you can say that the linear momentum of a body is obviously equal to the product of the mass and the velocity. Mathematically, you can say that for momentum we use the letter P, for mass M, and for velocity V. So momentum is the product of the mass and the velocity. Obviously, the SI unit of momentum will be kg meter per second, and the CBSE unit will be obviously dyne centimeter per second. Remember that both force and momentum are vector quantities. Force and momentum are vector quantities, and mass is a purely scalar quantity, because with momentum it is the direction of motion that is associated, and with force also it is the direction in which the force is applied. So if you consider the change in the momentum of body, either the mass will change or the velocity will change or both will change. But for making things simplified, we often assume that mass is constant. But in reality, there are some situations where mass may not be constant. Say for example, an oil tanker is moving and somehow oil leaks from the tanker. Definitely, with time the mass of the oil tanker is decreasing with time. From a truck loaded with sand, sometimes sand spills out, for which you can definitely realize that the mass of the truck, the effective mass of the truck with all the sand in it, is decreasing with time. So there are situations where the mass is not constant, but for mathematical simplicity, for most of the examples or most of the numericals that we solve, we assume that the mass is constant. However, by change in momentum, we should realize that it is the mass that can change, it is the velocity that can change, or both can change simultaneously. So if you consider change in momentum, let me denote the change in momentum by the symbol delta p. Then this change in momentum is actually the change in the product of mass and velocity. Now if mass is constant, if mass does not change, if the mass does not increase or decrease with time, then it is quite easy to say that change in momentum is equal to mass into change in velocity. Now this is what makes our mathematical analysis more simplified. But still I will show how mass changes with time and what is the effect of the change in mass associated with the change in momentum. So change in momentum is equal to change in the product of mass into velocity. As I have already said that if mass is constant, then this change in momentum is equal to mass into change in velocity. If mass is not constant, if mass is not constant, then this change in momentum is equal to mass into change in velocity plus velocity into change in mass. Now this situation will only arise if mass is not constant, if mass is increasing with time or mass is decreasing with time. I have already given some examples. Apart from those examples, in the case of atomic particles which are moving with a very high velocity, not only atomic particles, but if any particle is moving with a very high velocity, a velocity that is comparable to the velocity of light. If a particle, if the velocity of a particle is comparable to the velocity of light. The velocity of light is denoted by c and it has the value approximately 3 into 10 to the power 8 meter per second. Now this is not a common situation. This will never occur anywhere in our daily life. Now this occurs in case of particle accelerators where particles are accelerated to very high velocities, and those subatomic particles can acquire velocities which are very close to that of light. In those situations, the mass changes with velocity, and there is a very common mathematical expression that demonstrates how mass changes with velocity. Now this is not to be discussed anywhere unless and until you realize what is relativity. Still, for curiosity, if anyone has any curiosity regarding how the mass changes with changing velocity, here V represents the velocity of the subatomic particle and C represents the velocity of light. If the velocity of the particle is very close to the velocity of light, then the mass of the body increases with increasing velocity, and it is given by this expression. Here m0 is called as the rest mass. That means it is the mass of the particle when it is at rest, and when it is at velocity v, its mass is m. So now this is much beyond the scope of our syllabus, so we will not discuss this anymore. But for ordinary situations, mass might change. A truck is leaking some sand, an oil tanker is leaking some oil. For rocket propulsion also, you can see that whenever the rocket raises from the surface of the earth, it exhausts a large amount of gas, due to which its mass continuously decreases with time. And in those situations, we will realize that the change in momentum is mass into change in velocity plus velocity into change in mass. Now if I divide this equation by change in time, this equation, if I divide by the corresponding time interval during which the change is occurring, the change is occurring in a definite time interval. So if I divide this by change in time, delta t represents the time interval, I will get change in velocity by change in time plus V, change in mass by change in time. Now this change in momentum in a given time interval is the force acting on the body. Remember this, I will come across the change in momentum in a given time interval in Newton's second law of motion. But change in momentum in a given time interval is nothing but the force. And change in velocity in a given time interval is nothing but the acceleration. So this is an expression for the force, where force is equal to rate of change of momentum, and the acceleration is definitely the rate of change of velocity. Again, from this expression, if mass is constant, if mass is not changing at all, then you can say that this quantity, change of mass in a given time interval, is 0. Mass does not change means delta m is 0. So, for that situation where the mass is constant, this term delta m by delta t is 0, which means F equal to ma. So this is the very popular equation, which is also called as Newton's second law of motion. And now that Newton's second law of motion, it states that a force is necessary to change the state of motion of a body when it is applied on it. The force produces acceleration in the body. The force is the cause of acceleration. Similarly, when you are trying to bring a moving body to rest, it is also a force. Say for example, friction or air resistance is required to stop a moving body. In that case, the body retards. So acceleration or retardation is produced definitely by a force. And so, by Newton's second law, or the statement of Newton's second law, will be something like this. The rate of change of momentum, if you observe this expression minutely, F equal to delta P by delta T, from that you can state what is Newton's second law of motion. It says that the rate of change of momentum is directly proportional to the applied force, and the change in momentum actually takes place in the direction in which the force is applied. And this becomes the mathematical statement of Newton's second law, from which we get this final equation, F equal to ma. So Newton's second law of motion states that the rate of change of momentum is directly proportional to the applied force, and the change in momentum takes place in the direction of the force applied. So you can say that the applied force F is directly proportional to the rate of change of momentum. Rate of change of momentum means change in momentum in a given time interval. Change is denoted by the symbol delta. Now there is a proportionality symbol here. Also we can say that F is directly proportional to change in the product of mass and velocity. Because momentum is the product of mass and velocity. Now, in order to remove this proportionality symbol, we multiply the equation with a constant. Now this constant is K, and when we choose the definition of unit force, by the definition of unit force, now unit force means a force that causes an acceleration of 1 meter per second square in a body of mass 1 kg. We get the value of K as 1. So by the definition of unit force, this K is taken to be 1. Unit force means a force of 1 Newton acting on a body of mass 1 kg and capable of producing an acceleration of 1 meter per second square. So by this definition, K is 1, and so you can say that F equal to if mass is constant, we write it as F equal to m delta V by delta T, and finally we write F equal to ma. Since acceleration is rate of change of velocity, delta V by delta T is acceleration. So this is the statement of Newton's second law as force equal to mass into acceleration provided mass is constant. This relationship holds good only in two situations: whenever the mass is constant and when the velocity of the particle or the velocity of the body concerned is much smaller than the velocity of light. This is a point to be remembered, that this equation F equal to ma or this equation, they are exactly the same, and these two equations hold, they are true whenever the mass is constant and the objects that we are dealing with are moving with velocities which is much smaller than the velocity of light. Now, from this equation F equal to ma, we can analyze the variation of the mass, the acceleration and the effect of the force on different objects. So, if I draw a graph which compares force versus mass or mass versus acceleration, suppose we try to compare, or we want to know the dependence of acceleration with the force. Suppose we plot acceleration along the y-axis and the force acting on the body along the x-axis. We are applying this equation F equal to ma, and if you say that mass is constant, obviously in this case the mass is constant, this equation says that mass is constant, then you can say that A is directly proportional to F. That means that the acceleration produced in a body is directly proportional to the force, which means more is the force, more will be the acceleration, provided the mass of the body does not change. So the graph between acceleration and force will be a straight line passing to the origin, provided mass is constant. Now, if you want to know the dependence of force on mass, so suppose we draw a graph with force along the x-axis, along the y-axis, and mass along the x-axis. Now, if we assume that the mass is changing, but acceleration is constant, we are using this equation F equal to ma, and we assume that acceleration is constant. That means on different bodies, on different objects of different masses, we are applying different forces that are producing the same acceleration. Suppose you consider a bike and a car. Both are of different mass, but suppose they are all moving with the same accelerations, that is, say 10 meter per second square. So different forces has to be applied. So if acceleration remains constant, it is obvious that the force is proportional to the mass. So more is the mass, more will be the force required, provided the acceleration is constant. And hence the graph between force and mass will again be a straight line passing to the origin. Here we have assumed that the acceleration is constant. Now this is just a comparative study on objects of different masses, and in the previous case on same type of objects whose mass is same, but we are applying different forces that produces different acceleration. Now, in this case, this graph should not in reality pass to the origin, because if it passes to the origin, it means that there is no mass. So precisely this graph has a tendency to pass to the origin, but in reality, if it indeed passes to the origin, that means that the mass is zero, which is impossible. These are the two comparative study of the relationship of acceleration with force and force with mass. On a similar basis, we can also compare acceleration and mass. So if we again plot a graph between acceleration and mass, suppose acceleration is plotted along the y-axis and mass, the value of different masses, is plotted along the x-axis. We are using the same relationship F equal to ma, but here we constant the force as constant. The same force is being applied on objects of different masses, and definitely more will be the mass, lesser will be the acceleration. If you apply the same force on a truck and you apply the same force on a car, definitely a car will accelerate more as compared to that of a truck, because a truck has more mass. So more mass means lesser acceleration, lesser mass means more acceleration, provided the same force is applied. So the graph will be a hyperbola or hyperbolic nature. This graph will never touch any of the axes, so the nature of the graph is hyperbola. The nature of the graph is hyperbola, unlike the previous cases where the nature of the graph was a straight line. So from this discussion, the conclusion is that Newton's second law of motion is the actual law of motion or the fundamental law of motion. Newton's second law is the fundamental law. It means that we can obtain the first law from the second law itself. Newton's second law is the fundamental law. Law of motion. That means we can obtain the first law from the second law itself. And as we progress, after we learn the third law, we can also realize that the third law can be obtained from the second law also. That's why it is called as the fundamental law of motion. So, if you look at the statement of Newton's second law, since force is equal to mass into acceleration, provided the mass is constant, if we have no force acting on a body, if the force acting on a body is zero, or if the sum of all forces acting on a body is collectively zero, then obviously acceleration is zero, since mass is not equal to zero, because you cannot have any object with no mass at all. So if F equal to 0, then A equal to 0. Now this means that a body at rest will remain at rest and a body in motion will remain in motion, which is nothing but the statement of the Newton's first law. Acceleration is 0 means that the body is either at rest or is moving with uniform velocity. This means that a body is either at rest, because no acceleration means either at rest or moving with uniform velocity along a straight line. Uniform velocity along the straight line. And this is nothing but Newton's first law of motion, or the law of inertia, which says that a body maintains its state of rest or uniform motion along a straight line unless and until it is acted upon by forces on it.